We're going to talk about polynomial functions some more. Let's talk about what it means to put a polynomial function in standard form. So when you have the function in standard form, you basically have the terms arranged so that the exponents are in decreasing order. So for example, with the quadratic equations, it was f of x equals x squared minus 3x plus 1. And if you look at the exponents, it goes 2, 1, 0. That's what it means to put something in standard order, in standard form. If it's a higher degree, so it'll be like x to the 5, and then the fourth term, and then x to the 3, 2, 1, 0, and so on. Now, once you have it in standard form, the first term is going to be the one with the highest exponent. And it's like the line leader. We call it the leading term. So that's always the one with the highest exponent. The coefficient of that leading term is called the leading coefficient. So in this case that I've circled, what would the leading coefficient be? Of the x squared, it'll be a 1, right?
So you always start with the leading term because it goes in descending order.
Well, once you put it in descending order, it's not always going to be given to you in standard form. So you have to put it in standard form, and then once you do, the term with the highest exponent is the leading term, and it's got the leading coefficient. Okay, now we talked about degree before. The degree of the polynomial is the degree of it's the greatest degree of its terms. All right, so let's talk about some different types of polynomials. When I have a function that looks like this, so let's say y is equal to 12, okay? Well, where is the variable here? It looks like there is no variable, but was there a variable at some point? The variable here is really x to the power of 0. What's anything to the power of 0? 1. So here, there is a variable. The exponent of it is 0, so we just don't happen to write it, okay? So the highest exponent here is a 0. That's why we say that the degree of this is 0. So anytime you have a function that looks like this, y equals 12, y equals 7, f of x equals negative 3, where it's just a constant, the degree is 0. Now, let's talk about a linear equation. A linear equation is one that looks like this. These are all your mx plus b's, right? What's the highest exponent that shows up here? It's x to the power of 1. Here we have x to the power of 1, so the degree is 1. And what about our quadratic functions? We're experts on that now. What's the highest exponent? 2, so the degree there is 2. In a cubic function, which we haven't done too much of, the highest exponent is 3, so the degree is 3. All right, so that's how we figure out degrees. Now, the term that carries that highest exponent is the leading term. So this is the leading term, and that coefficient out front is called the leading coefficient. So in the case of the cubic one, what is the leading coefficient? 8. It's always the coefficient of the term with the highest exponent, so it's an 8. Well, what about the case of the quadratic equation? What would the leading coefficient be? 5. Okay. What if you had the constant? What's the leading coefficient? It's just the constant itself. It's 12. All right. So let's take a look at example number 1. What is the degree of this polynomial? Highest exponent is a 6. So this is the term that gave us that exponent, right? What would the leading coefficient be then? The 5. All right. Okay, so let's take a look at this next one. We need to find f of 3b if f of x is blah, blah, blah. And we have done similar ones to this before. So if I want to find f of 3x, f of 3b, sorry, what do I need to do? plug in what for each of the x's? Plug in 3b for each of the x's. So 3b squared minus 2 times 3b plus 5. All right, and now let's simplify this. Who does that square belong to? The 3 and the b. So this is going to be 3 squared, 9, b squared, minus how many b? 6b plus 5. And then you just have to check. Are there any terms I can combine? No. Is it in standard form? Are the exponents going down? Yes. So we're good to go. So that's f of 3b. Okay. Now, look at this next one. It's taken up a few notches.
So that's all you do? You don't have to, like, if that
We don't
if
factor.
you put it in function format, it's not find the leading term, it's just
Right.
that.
We just simplified. Okay, now we need to do 2 times f of 3x minus 5. So look at this one. I have 2 times, right, f of 3x minus 5. Oh, sorry. So it's f of 3x minus 5. Oh, that does change it. Okay. Thank you. So then we have minus 5 out here. Okay. Okay, so f of x is this function here. So this is 2 times, well, what's f of 3x going to be?
2 times 3x.
It's 2 times 3x squared minus 3x plus 1. Minus 5 outside, right? Okay, so now let's simplify. This is 2 times, how much is this? 2 times, how much is 3x squared? 9x minus 3x plus 1 minus 5. So this is 2 times, how much? 18x minus 3x plus 1 minus 5. Okay, now what am I going to do? Distribute the 2, so I get 36x minus 9x. Oh, this was an x squared. Sorry, that was an x squared.
Why would it be x squared?
Because it's 3 squared and x squared from the very beginning. 3 squared and x squared. Okay? So minus 9x plus 2 minus 5. And now it's 36x squared minus 9x minus 3. And even though there is a factor of 3 you can factor out, you don't have to. All right, so this next one, we need b of 2x minus 1 minus 3b of x. All right, so I'm going to divide and conquer this one. I'm going to make it 2 mini problems and then combine them. Okay, so the first one I have is this one in the green. And then I have another one in the blue. All right, so let's just do the one in the green first. What does it ask you for? It asks for b of 2x minus 1, right? Okay, what's b of x?
2x squared plus x.
Right, so it's going to be equal to 2 times 2x minus 1
Why 2 times?
squared. Okay, so I'm plugging it into b of x, which is 2x squared. So it's 2 times x squared. I'm plugging it in there. I'm plugging 2x
X
minus 1.
is 2x.
Right. And then plus x was 2x minus 1 minus 1. Okay, so this is 2 times. Let's open up a new parenthesis. Okay. I'm going to square the first term. What am I going to get? 4x squared. I'm going to square the last term. What am I going to get? Plus 1. Okay? I square the first term, I get 4x squared. I square the last term, I get 1. So basically, we're foiling, but we're using the shortcut. You can very well do 2x minus 1 times 2x minus 1. You're going to get what we're going to get here. Okay? Now, the middle term, I'll get you in a minute. The middle term will be 2 times minus 1 times 2x. 2 times minus 1 times 2x, which is negative 4x. Here we have plus 2x minus 2. Now, let's multiply in the 2. So I get 8x squared minus 8x plus 2 plus 2x minus 2. Okay, what can we simplify here? Right, so it's 8x squared minus 6x, and that's it. Okay? Okay, so I did the green part. Woohoo. I'll circle it or put it in a square. All right, now let's do the blue part. It's just 3bx. The negative I'll keep for later, yeah. So 3bx, it's 3 times, how much is b of x? B of x is 2x squared plus x minus 1. So how much will that be? 6x squared plus 3x minus 3. All right? Huh? Not yet. Okay, now what are we going to do? Is everybody... It's 3 times b of x. 3 times, this is b of x, so it's 3 times b of x. Now, what did I have before? I had the green. Right, so I kept the negative for later. Now I'm going to use the negative. So what do I have before? I have the green minus the blue. Okay, can I do that now? So what's the green? It's 8x squared minus 6x minus the blue, which is this. Okay? All right, so finally, let's simplify. It's 8x squared minus 6x. Let's distribute the negative. So, can I combine anything here? 8x squared and negative 6x squared, what do we get? 2x squared, negative 6x, negative 3x, what do I get? And then plus 3. So that's the final answer. Now, the ones on the homework will not be as difficult. I throw this one in there so, you know, we turn it up a few notches and then we can get back for the homework so it doesn't feel as overwhelming when you're doing the homework. Okay, let's do some graphs of polynomial functions. All right, so if you have a degree of 0, so for example, y is equal to 3, all right, what does that graph look like? Well, if this is y equals 3, then y equals 3 is just a horizontal line through y equals 3, right? And now if you have a linear function with a degree of 1, this is your basic y equals mx plus b. And we all know what those look like. It's our favorite. Well, maybe now our favorite is the quadratic function though, right? With a degree of 2. And you know that looks like a parabola, either facing up or down. So these three we've seen before. Now, well, what if you have a cubic function with a degree of 3? Well, what happens here, let's see the pattern. So this one is going up or down like this. When you have a degree of 2, there is a point where the function turns around. You see that? When you have a degree of 3, what happens? How many times does it turn around? Twice, right? It turns around twice. When you have degree of 4, it turns out more times. It turns out more. So 3 times. And then degree of 5, similar. How many times does that turn around? 4. Okay. And we can probably come up with a pattern between the degree and the number of times it turns around, right? Do you guys see a pattern?
One less.
It's 1 less. So that's a pre-calculus thing, and you guys just got it all on your own. So way to go. Now let's take a look at some other patterns. So I want you to specifically focus on the graph for a 3rd degree and the graph for a 4th degree. Anybody notice? Let's think about what similarities and maybe what a difference that we can come up with. So if the degree is odd, then the ends go in opposite directions. One goes up, one goes down. Here too, with a degree of 5, one end goes up, one end goes down. But if the degrees are even, then they either both go down or they both go up. Okay? Now, let's make a few more conjectures here. So suppose we have a function with an even degree, like your x squared and your x to the 4 and your x to the 6. And now these LCs stand for leading coefficient. Okay? Now, let's just take the small one, the one we're most familiar with, the x squared. Okay? If the leading coefficient, so if I have something like this, what is the leading coefficient there? That's a 2. If that leading coefficient is positive, what do we know about where the ends are going to go? Up. So both go up. Okay? And what if the leading coefficient is negative? They both go down. Both ends down. Now, let's take a look at the odd functions, x cubed, x to the 5, x to the 7, or even x to the 1, okay? If you have a positive leading coefficient, like 3x cubed, 3x minus 7, what happens? One end's going to go down and one end's going to go up, but which one goes up? The one to the right will go up, right? So right end goes up, and left will go down. Well, what if the leading coefficient is negative? So what if I have like negative 3x plus 1? The left end is up, and the right down. Now, we can sit here and draw arrows all our life. However, we got to now put it into mathematical format and use mathematical symbols, right? What we call this and what you guys just came up with all on your own is called end behavior. And this is something that's huge in math, all right? End behavior is very telling about what a function will look like, how it'll behave, and it's got so many life applications. So first of all, when you're dealing with polynomial functions, all right, these are the functions like the ones we're talking about. The domain for them is always all real numbers, right? Just like with the parabola, the domain is always all reals. Now, the end behavior says whether it's going to go up on the right or it's going to go down on the right and so on. So I have a little volunteer here who helps me with this. He's called Mr. Polynomial. There's Mr. Polynomial, okay? Mr. Polynomial just walks all along the x-axis. He just keeps going to the right all the way, and then he turns around and he goes to the left all the way. So suppose he's moving to the right, okay? He goes to x equals 4 and then moves on to x equals 100 and moves further to x equals 1,000,000, and now he's all the way at x equals infinity or close to that. The whole time he's got his eye on the graph. And as he's moving to the right, okay, he sees this graph, right? Where does he see the graph going? Is it going up or is it going down? It's going up. So what we say is, as x approaches positive infinity, as Mr. Polynomial approaches positive infinity, the graph, which is f of x, also approaches positive infinity. Now, what if Mr. Polynomial turned around and now he's going to the left? And he's going all the way to negative infinity here. Where does he see the graph going? Up or down?
Down.
Up. Up again to positive infinity, right?
It's going left.
As he's moving here, we're looking at this particular graph. As he's moving here, the graph is going up. Okay? So as x approaches negative infinity, the graph approaches positive infinity. All right, let's do an actual example, because again, we can look at this chart all we want. Yeah. So this example, right? This is an example of a graph. Normally, that's what you're going to run into. So first of all, it asks if the function is odd or even degree, right? What do you think? Odd or even? Odd. Why is it odd? Because one side goes up while the other side goes down. Okay? Okay. How many real zeros are there? This is the number of times it crosses the what? There you go. What other words do we have for zeros? Solutions, roots, and x-intercepts, right? Okay, so how many real zeros are there? One, because it only crosses the x-axis one time. Oh, we forgot b. So what is the degree of this? What would you say is the degree of this? 3, right? Why? Look at how many times it turns around. So one time here and another one there, and it's always going to be one more than that. So 3. So it turns around. If suppose you're on a roller coaster here, it turns around there, and then it turns around one more time. It turns around twice, and the degree is one more. Okay. Estimate the real zero, right? So the real zero is between -2 and -3. Okay, so when we're doing this, the scientist in me takes over, and I think about sig figs, and the most precise here as we can go is to the 0.5s. So it'll be -2.5. So we can't estimate like 2.2 or 2.3 or whatever.
It's only 0.5.
Yeah. It's only 0.5 increments. Now, describe the end behavior. End behavior. For end behavior, before you even look at the end behavior, first set it up. And the way we set it up is this. As x approaches positive infinity, f of x approaches some blank that we're going to fill in a minute. And then as x approaches negative infinity, f of x approaches some blank that we're going to fill in. Okay? Every single question with end behavior is going to have all of these, identical as you see here. The only difference is now going to be what we're going to fill in. So, let's see. Here is our Mr. Polynomial. As I'm walking to positive infinity, is that to the right or to the left? As I'm walking to the right, I have my eye on the graph. Where is it going? Is it going up or down? If it's going up, does it go to positive or negative infinity? Positive infinity. There we go. Now, as I go to the negative infinity, now I'm moving to the left, and I have my eye on the graph. Where is the graph going? It's going further and further down to negative infinity. So there we go. That's my end behavior. So that
The graph goes where?
all of this is the answer. All of this is the answer to E. Okay? All right. So that's the homework for this section.